Hey folks, Mike here. I noticed that in the last, someone told me in the last example of the last video, I made a mistake, and this 9.0 should have been 0.09, so I was off by 100 times. And I found in my life the way to deal with my mistakes is I just make them disappear as soon as possible. So this mistake is going to undergo some oxidation. You know what? Oh, hold on, wait a second. I think I know a way I can make it disappear faster. There, and now you see, now that I've divided the mistake page up into smaller particles, that's just good surface area. That's a lot more surface area. And now I can just watch it disappear much quicker. So, there. What mistake? I don't remember any mistake that I made, thanks to higher surface area, and now that's going to disappear a lot faster. Alright, today we're going to talk about first order reactions and half-life, so let's go do that right now, or after a little while, after I make sure everything's gone, all the evidence. Well, hello everyone. Hello, Mike here. I'm here to talk to you about more kinetics. And by the way, my mistake, I apologize for that. I was off by only 100 times. It's not like that would kill anybody if I was a pharmacist or something. Okay, so let's talk about the mathematics. Well, by the way, it's nothing but mathematics for a long while here, of first order processes. So let's look at what we know already. We've been talking a lot about rate. So this is where, if you had the molecules, and we're going to make things simple, just say it's A goes to make B. So A is the reactants and B is the products. And we're told, or have determined already, that somehow this process is first order. Now, for a bunch of things, a bunch of reasons that you don't have to worry about, let's even go ahead and just use this word, and I'll tell you why we don't have to worry about it. Calculus. All right? And you can like that or not like it, but we don't have to. It's not part of the core curriculum here in General Chemistry 2. But thing called the derivative is what a rate is. It's a rate, it's telling you how much progress per time. And if you do what you call the integral, and that's why they call this an integrated rate law, instead of rate versus concentration, which that would be rate versus concentration, or concentration versus rate, you now have a function of concentration versus time. And now the nifty thing is, if you go and keep track of the units here, this is a natural logarithm. This is the concentration at any particular time. This is the concentration at time 0. So if you think about it, this is a reactant. It's going to disappear. And this fraction is between 1, that's the maximum it could be if the concentration was the initial, and 0. So it could go down to 0. And this is the math that describes a curve where we start out at an initial concentration, and then we kind of decay from there. But as the reaction slows down, you never get to 0. And so that's sort of the mathematics of any point on this graph. That would be concentration of A at any particular t time. And so you have this function. But just kind of to ground you, remember that you can't have this fraction be, first of all, it's unitless. This could be moles per liter divided by moles per liter. It doesn't even have to be in any particular units, just the units must be the same. So this could be grams over grams, but you notice that it's going to be unitless on the left. This is going to be in units of time. And then if you're dealing with a function, you're going to find out that the units on both sides of the equal sign have to have the same units. And so if this is unitless on the left, this must be in units of inverse time. So this could be seconds, and that would be 1 over seconds. This could be hours, and that must be 1 over hours. And so that's another little tip of the hand, is if sometimes a problem will be like, hey, this is K. This unit of K, that's called the rate constant, as we said before. It's going to tell you whether it's first order or second order based on its units, and we'll talk more about that in the future. But if this here, the concentration of rate, or the units of rate were moles per liter per time, and this would be moles per liter, then you see that this would be 1 over time. So it's consistent. No matter what equation you use, it's the first order equation, the one I wrote here, rate versus concentration, or concentration versus time. The units of the rate constant are the same. All right, pretty mathy stuff, but once you get used to a few reps with the equation, like we're going to do next, you'll find out it's pretty comfortable. So let's use an example problem that I dug up just next. You're probably looking at this like, why all those words, Mike? And that's because a lot of these problems get pretty verbose, and I don't want to make any judgments about that. It could be somebody at the old textbook company is professionally frustrated, but the bottom line is you're scanning through these like a computer, and let's see what we glean from this information. So I'm going to go and I'm going to read this, and I'm going to literally in my mind say blah 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 blah. And no, look, I'm not saying that I'm not sensitive to things about oxides in the air. It's just that I'm looking for information, and this is all just stuff that's fluff that I don't need to solve the problem right now. I can go on my own time and look up about dinitrogen pentoxide on my own time, but I'm looking now and I see blah 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 first order. That means I have to use the first order equation. Whatever this problem is, it's going to require, let's get rid of the blah blah blah. The tool is natural log of concentration of N2O5 divided by concentration of N2O5 initial equals minus KT. That's all I've gotten with all that blah blah blah. Here's a reaction. Okay, great. That told me what the reactant is. K, bang. So we know what K is. If K is that, there's the units of K, 1 over time, and the initial concentration is 0.35 molar, and that means concentration of N2O5 initial is that. What is the concentration after 3 minutes? Let's crank some numbers out. So what are they asking? What is the concentration at 3 minutes? That's this. And so we're going to plug some stuff in. And you're going to need one of these bad boys. So let's go ahead and do that. So the next step for me, ooh, something just popped up that's kind of juicy. I'll explain that in just a second. Natural log of x, because I don't know it, divided by 0.375 equals minus 0.00693 inverse seconds times 3 minutes. Now, let me say this. Here's something that's just waiting to rear its ugly head at you. If you don't have that in units that are complementary with the rate constant, then you're going to jack it up. And now, by the way, what's the result of this? I don't know what x is yet, but I know it better be less than 0.375. And so if you put the wrong number here, like 3, because 3 minutes is 180 seconds. Ha ha, problem. You tried to trick me, and you didn't get away with it this time. All right, and so I'm going to go ahead and say that's 180 seconds. And I have the ability now to get a result on the right and not yet on the left. So let's talk about what we can do. Order operations, I can say 0.00693 times 180. That's going to be a unitless number, by the way. So pushing onward, natural log of x over 0.375, darn, 0.375 equals minus, now watch out for that minus sign, because it turns out that minus is always what happens when you have a natural log of something less than 1. 1.2474. Now it gets a little tricky. What you're going to have to do is, first of all, I need to make that minus. You're going to have to make friends with the inverse natural log button on your calculator. So you got a natural log button, and you'll notice usually the second function of that is an e to the x. And that's because, long story short, a natural log undoes a e to the x, or an e to the x undoes a natural log. Either way, you get that back. So what I need to do is an inverse natural log, or an e to the x, of both sides, and I can do it to the number, and I'll do it right now. It's for my calculator, it's the second function, e to the x button, 0.287. Now that sounds pretty cool to me, because I know that that fraction has to be below the value of 1. It's always a fraction that's 1 or less. And so what that does over here is that just gets rid of the natural log. So it's x over 0.375 molar equals, now the result of that was 0.2873. 0.2873. And so a quick little bit of simple algebra would be to multiply both sides by 0.375, and I get 0.1077. Given 3 digits, let's say that that's x is equal to 0.108 molar. So the concentration has diminished to about what we would call, I'd say, a little bit less than 1/3 of the value at that particular time. Now, what you should be able to do is look at this, and it might not make complete sense, like, oh, that makes such great sense. But what it could do is you could at least feel sort of good about yourself, because you could say, well, as a result of this, I know that the number should be less than the initial, which is 0.375. And so, these things aren't always as intuitive until about 10 seconds from now, when I talk about how they're going to be intuitive. And that's using a tool that's used with first order processes called the half-life. So let's talk a little half-life and do a derivation of half-life next. All right, folks, we're going to talk some half-life. And you may have heard of half-life. It's a good way to sort of make some of this stuff relatable. And so let me first talk about what half-life is sort of qualitatively, and then we're going to go ahead and talk about how we talk about the numbers of it. So first of all, I want to clear something up. This is only useful for something that's first order. It really, well, I'm going to be honest with you. It really kind of pisses me off when I see textbooks say, what's the half-life of this thing, and it's second order. And this is why. It just confuses people. Only first order processes cut themselves in half at regular intervals. So here's our concentration, here's our time, this concentration of A, this is T, and then what happens is here we got initial, this would be 100%, and then what happens is after a certain amount of time we get to 50%. That's half. And this would be something we call T1 half. So half-life is a time. It is the time required for concentration. It could be concentration, it could be the amount, it could be the mass. So for reactant, whatever measure you want to use, to diminish to 1/2 initial. I don't want to say concentration because it could be mass, it could be whatever. That's the definition of what a half-life is. Now the thing that's unique about first order and not anything else like second order is that after the same amount of time, let's take that distance in. That 50% is like the new initial, and it's going to cut itself in half again. And this would be 2 times T1 half. And that would be at 25%, which is half of a half. How about another half-life, like 3? Now we're at 12.5, which is half of a half of a half. So we're at 1/8. You know, 1, 1/2, 1/4, 1/8, 1/16, 1/32, and here's the trick question. When do you get to 0? Never. You never get to 0. And so, but it's a curve that asymptotically, pretty sure it's a word, approaches 0. And it's really, you're just dealing with multiples of 1/2, where x is the number of half-lives. This is not what happens with second order, so no matter what you read in a textbook, second order, that interval, you can call it T1 half, but it's going to be a different number the next cycle of half-life. And so it's really only useful to sort of ground you in terms of solving problems. So I could say, hey, this problem right here, what we're going to do next is we're going to go and solve for the half-life of it. You know, and there's a relationship. But I could say that half-life would take that down to, I don't know, a little bit below what 0.375 divided by 2 is 0.1875. That would be 1 half-life. Divided by 2 again would be 0.09. So that result there, I could say that's somewhere between 1 and 2 half-lives is what time I'm at. And how do we do that? Okay, so there's a really quick, simple derivation here using the first order equation. And you can do this whenever you want because, whoopsie, that wasn't a 0, that was supposed to be. You can do this whenever you want. All we're going to do is we're going to say that there's a condition at t equals T1 half. What's true there? Well, according to the definition of half-life, the concentration of A will be 1/2 initial. So let's plug in T1 half for T. Let's plug in 1/2 A initial, and it gets to be really kind of simple. This is natural log of 1/2 concentration of A initial divided by concentration of A initial equals minus K times T1 half. Look what happens. The concentration of A initials cancel, and it just ends up being natural log of 1/2. And if you go plug into your calculator, 0.5, hit the natural log button, you get minus 0.693. So we have a new relationship here. And that is minus 0.693 on the left equals minus k times t1/2. Now why don't we just go ahead and get rid of the negatives, because there's double negative, and so that would be 0.693 equals k times t1/2. K is your rate constant. That hasn't changed. So you got two nifty little relationships that are born out of this, and that is k, if we solve for it, equals 0.693 over t1/2. Or, let's solve for t1/2. t1/2 equals 0.693 over k. So, if you wanted to, you could solve, if you're given k and it's first order, you can interrelate between the k constant, which is, you can't look at a k constant and say, oh, I get that. But you can look at a half-life and say, oh, that's when it cuts itself in half. And that's when it cuts itself in half again. And so what we're going to do now is we're going to use this, we're going to say, let's go solve for in the last problem. Let's go solve for what t1/2 is. They gave us a k. It was in seconds. So in this particular instance, I could go and take and use my k value, 0.69. Well, I want to solve for t1/2, my bad. So I'm going to go ahead and I'm going to solve for t1/2 using the numbers that they gave me in the problem. But before I do that, oh, that was cute. 0.00693 inverse seconds. See what they did? Someone was really either not being creative when they wrote up this problem, which makes me wonder if this is a fudged k value that was out of this book that I liberated this problem from. Because, and it's one, I'm not going to say which book, in case they have a team of lawyers that wants to come out. That is 100 seconds. Okay, what if I knew this information ahead of time? What if and I could have said, okay, they said it was first order and they gave me a k, and then the question was, what's the concentration after 3 minutes? And I could say, well, 3 minutes is 180 seconds. It's going to be about a third. It's going to be about a quarter or a little bit more, because what's going to happen is 180 seconds is a little bit more, or a little bit less than 2 half-lives. And so I know that the initial concentration was 0.35 molar, and that therefore, I could say, well, half of that would be after 100 seconds. And then so my answer should be something in between what is a quarter and a half of the initial concentration. So you see, that's a much easier way to think about it. So much so that we're going to use half-life. This 100 seconds we're going to use to solve one more problem. I know this has been a long journey today, but we're going to do just one more example problem, and then we'll cut you loose to let you practice more. All right, so let's consider this to be an add-on to the last problem, where they gave us the k, and they're going to say how long, okay, once again, how long is going to be a t. I need to solve for t. Does it take, how much time required? Probably. I kind of just sort of got, not so articulate with this problem when I dreamed it up. How long does it take? How long required? How much time required? Now this is kind of one of those things. Carefully, you got to read this. For 95% of the N2O5 to decompose, that really means that there's 5% left. Don't let that kind of thing fool you. 5% left. That means 95% of it has decomposed, and this would be an extension of this problem. And before we get going with the k, here's what I'm going to do. I'm going to plug it in to the equation, which is natural log of concentration N2O5 divided by concentration of N2O5 initial equals minus, now they gave us the k in the previous example, and it is minus 0.00693 and times t. And what's going to happen is and remember, it doesn't matter what these units are. 5%, 100%. Can it be in units of percent? Yeah, it can be units of anything. They just got to be the same. Now, let's think about what that is. 5 100ths is 1/20th. 1/20th in half-life world is between 1/16th, which would be, okay, let's think about it. 1/2, this is my finger. 1 half-life would be 50%. 2 half-lives would be 25%. 3 half-lives would, and that would be, 1/4. 3 half-lives would be an 1/8 left. 4 half-lives would be a 16th left. And 5 half-lives would be a 32nd. So 1/20th is somewhere in between 1/16th and a 32nd, 1/32nd. And so my answer better be between 4 and 5 half-lives, so it better be 400 and some seconds. Pretty sure I said that right. 1/20th is between 1/16th, which is 4 half-lives, and 1/32nd, which is 5 half-lives. The answer to this problem is going to be 400 something seconds. I just predicted the future, which is the whole point of science. So natural log of 5% over 100% equals minus 0.00693 t. Okay, let's go ahead and plug in 5 divided by 100 is 0.05. Natural log of that is minus 2.9957 equals minus 0.00693 inverse seconds, Mike, times t. So let's divide both sides by negative 0.00. What if you forgot the negative? Oh, that's not good. You'd get a negative time. And that only happens in the movies with flux capacitors. And that was a Back to the Future reference. I know, it's pretty dated. So let's see what we get. I'm going to just get rid of the old negative sign. 0.29957 divided by 0.00693. Bang. 432 units now are seconds, because inverse seconds. And see, that's not half-life, but that was between 4 and 5 half-lives. And so you should be able to ground yourself and check yourself before you wreck yourself using the half-life if you're lucky enough to be given a first order equation. So the bummer is you got to think about logarithms with first order. Natural logarithms, just make sure you don't do anything that's perverted. Like, remember that fraction always has to be less than 1. But if you can solve for the half-life, you don't even have, the problem might not even ask you to solve for the half-life. You could just do it on your own and you could check your answer with that. On the other hand, though, they might give you a half-life in the problem, and I'm sure you'll run into those if you practice enough. And then you have to use half-life to solve for k, unless you are given the wonderful situation where what if this question here, instead of 95%, what if it was 75%? Well, then you'd go ahead and say that's 25 over 100. You wouldn't have to do anything with this natural logarithm stuff. You'd just say 25 divided by 100, that's 1/4. My answer is 200 seconds. 200 seconds for 75% of it to decompose. How long for 50% of it to decompose? 100 seconds. See, so you really, if you land on a multiple of a half-life, I've seen my students torture themselves by going and throwing it through this thing when, if you are fortunate enough that the writer of the problem has given you the time as a multiple of the half-life, life is good. You just say it's either half, quarter, eighth, 16th, and whatever multiple of the half-life it is, if they were giving you that fraction. Practice, folks. Don't let this stuff accumulate to where you have not practiced it, and then it starts, when you lump it on top of each other, all in a big, huge sort of huge. I don't know. Just practice it often and don't let it accumulate, because if you gorge yourself on this, it's going to be a bummer. It's all going to start becoming blended together. So we'll talk about second order next time, and there's a different equation, and that will hopefully be treated differently in your mind if you let this land in there now in a firm way. See you then, folks. Take her easy.